In this video, we're going to be introduced to the notion of a non-informative prior distribution. And as its name implies, this is a situation where we really have no prior knowledge about the parameter theta. Now, the reason why this is done is because of the attractiveness of Bayesian methodology. And as you can see in that last sentence there, we will see that this will sometimes lead us to what seems to be a quandary. So let's first look at the continuous case. So let's say that theta is our parameter of interest, and our data is x given theta, which follows a normal distribution. The unknown parameter theta is the mean of that distribution, and the variance is known to be 1. So I would recommend just think for a second. Okay, how would you put together a non-informative prior on theta? Now remember, this is a normal distribution, and so it's distributed over the entire real line. The parameter space is all of R. So I guess we would think naturally, or like our best guess would be to call pi of theta just some constant that's a positive number. But that's clearly not a valid prior density, because the integral of that over the entire real line is infinity, no matter what you pick C to be. So that is what we call an improper density, and it is used. And typically it is used where C is equal to 1. Seems to be a good choice for obvious reasons. That's called the uniform density on the reals, and was introduced by Laplace back in 1812. Now, in the case of finite parameter spaces, it's quite easy to derive a non-informative prior distribution, as we note here. In situations that was described where the parameter space is finite or a bounded interval, in a continuous case but a bounded interval of the real line, then we just use a uniform distribution. So let's just take the simple situation of a discrete distribution where there are only two possible values for theta. Then an obvious non-informative prior distribution for that would be one where we choose the one value with probability 1/2, and we choose the other value with probability 1/2. So neither value is weighted any more than the other. And if we had a finite distribution where there were only three possible values, then each one would be chosen with probability 1/3, and so forth and so on. And then similarly, as we mentioned before, if we have a continuous case, so if we have a bounded interval of the real line, then we would just use the uniform distribution.